Okay, let's start. So in the last class, we looked at the switch capacitor integrator, and this was the basic structure. We sample in one phase, and on the other phase, we transfer the charge to the integrating capacitor like this. Right? And if I sample this guy at the end of I1, what was the transfer function we get? It was C1 by C2, mind you. C1 by C2, and what is the transfer function? This is a delayed integrator or delay free integrator? Delayed. So we expect Z inverse by 1 minus Z inverse. And we also saw the delay free version. And there the only changes, you kind of sample and transfer the charge in the same phase like this and reset in the other phase. So here you get a negative gain without any delay, right? And the same thing can be done for the switch capacitor amplifier also. I'll just quickly show. So first let's look at the delay free one. So for the switch cap amplifier, I'll have to just reset the capacitor and connect it in every phase. So in which phase I will connect the capacitor C2 to the op amp? So it should be in phase 1, right? Because in phase 1 is when we are basically transferring the charge. So the capacitor also must be connected in phase 1. And in the other phase, you reset it. It's not very neat, but yeah, it should be clear. Right? So here in the, okay.
Before that, you are not overlapping that clock, right?
Everything must be, yeah. In any switch cap circuit, if you have multiple clock phases, everything must be non-overlapping.
Non-overlapping means one should not overlap with it.
Yeah. None of the clocks should be on at the same time. Basically, no two clocks should be active at the same time. That will screw up the circuit. So here the gain will be minus C1 by C2. So in the delayed one, in what phase I should connect the capacitor? In this circuit, in which clock phase I should connect the capacitor C2 to op amp? So in phase 1 we are sampling. It is in phase 2 that we are transferring the charge. So this should be in phase 2. And in the other phase, I will go and reset this guy. I mean, ideally you don't want a resistor. This switch will have on resistance, but besides that, there is no resistor.
Because of that, there will be some time constant.
Correct. Because of the switch on resistance, there will be a time constant, right? Yeah. But again, if you design it properly, things will settle within the available time. And here we are only interested in the settled value. So we can approximate that this is an ideal switch and do charge conservation. Right? And here in what clock phase I should be sampling the output? I should sample at 1 or 2. In which clock phase the capacitor is connected to the op amp? 2. So I should sample it in phase 2, right? In phase 1 the capacitor is reset. I lose the information. Okay. So if I were to make the information available in phase 1, I will basically have to buffer it once again and resample it in phase 1. Okay. So here you see that the signal is sampled in phase 1. We are transferring it in phase 2, and the earliest we can get the information is in phase 2. There is inherently a half clock cycle of delay, right? And by doing this, you introduce one more half clock cycle of delay. So overall, you get this as the curve. And I mean, this delay thing you also saw in the last class, right? So if you have something like this where you sample in one phase, do it in the next phase. If I do it like this, so first I sample it, transfer it in phase 2, and this again transferred in the next phase 1. So if this is V in, what will be this output? No. See, this input is there, we are sampling it. This is completely transferred to this capacitor in phase 2. And once again, this is same charge is transferred to the output capacitor in the next phase 1.
There will be a delay of one.
So basically, whatever input we are sampling, it's same thing will appear here after one clock cycle. There is no other operation happening because this buffer is simply buffering. This buffer is just forcing this voltage to this. No, nothing else is happening. So this will be what? If I were to write V in of, n minus 1.
That's how we.
Okay. Basically, see, from here to here you have half clock cycle of delay. Here it's 1 clock cycle of delay, right? That's all. And just because we have the buffer, no other operation is happening. Whatever signal we are sampling, we are simply reproducing it in every stage. So if that's the case, so let's say add, say, one more thing like this. So what will be the output here? N minus 2. Again, see, from 1 half clock cycle, 2 half clock cycles, this is third. So 4 half clock cycles of delay. So this is basically V of n minus 2. Right? So let's say I also do this. Let's say. So what will be this guy? N minus 1. Okay. Fine. So now let's say I make this. Yeah, I go ahead and connect these two. Okay. And once I have this, we have the same thing here, so I don't have to have two of them. So I'll disconnect this guy. So now what do you think will happen?
Plus of it.
Sorry, let me erase this. Yeah.
Just add both of these overs.
Yeah, but will it get superposed or so what is the final expression I can expect here? If I just had this path, what did I get?
N minus 2.
So let us say I had only this path. What will I get?
N minus 1.
N minus 1. So now what I am doing, I am basically connecting the two capacitors. So if I connect the two capacitors, there will be some charge transfer. So the output will be finally, something of the form alpha 1 times V of n minus 1 plus alpha 2 times V of n minus 2. So, right? You can find out what this alpha 1 alpha 2 is. Right? So, basically, see, it is nice to understand how to analyze circuits, but beyond some point, if you actually look at any practical circuit, it will be impossible for you to sit and analyze, right? So, you should be able to recognize small sub-circuits like this and qualitatively understand what the circuit is. And in this case, we can easily see this is giving 2 clock cycles of delay, this is 1 clock cycle of delay. We are kind of, adding the two, and you can work out the scaling factor, it's not that difficult. Okay. And of course, if you want to get better, you try to understand how the circuit can be synthesized from scratch, right? Let's say you understand this circuit is doing this operation. You see how the same circuit can be derived from this, right? So that way you will understand how new circuits are synthesized, and that's what will give you better understanding. That's why for the most part I try to build circuits from the scratch, not to just show it and explain. Right? Cool. And in the last class, I think we also looked at some history of switch cap circuits. So if you have time at the end of the class, I'll continue with that. But for now, we'll continue with other topics. So in all the switch cap circuits that we have seen, at least for the most part, we always assume that we have an ideal op amp like this. But of course, there is no ideal op amp. So we'll consider what are the non-idealities and how we tackle them, right? So what is the first non-ideality that you can think of? Input impedance is usually very large, right? Because it's a MOSFET. Usually it's very large. It's not a big problem. Yeah, but let's say, what do you understand by ideal op amp first?
So gain is infinite.
Gain is infinite. It's not possible to get infinite gain. So first, you'll get a finite DC gain, right? And basically that's like this. So let's say this is V2, V1. If this is V out, if the op amp has gain A, what is V0 in terms of V1, V2?
A times V1 minus
V1 minus V2 or the other way around?
V2 minus. Okay.
Plus minus the negative thing. So, okay. Now, the other non-ideality we'll consider is what he told. We'll consider DC offset. So this means that ideally you expect this as the relation, but in practice we'll get this guy to be V2 minus V1 plus some offset voltage. and this comes about, some of you might know, due to some random mismatches. So what that means is, if you take 100 different op amps and measure the offset, all 100 of them will have different offset voltages, but for a particular op amp it's constant, it's a DC, right? So again, to model this, what we do is the following: we assume that the op amp is all good, it has no offset, and the offset can be thought of as adding a series voltage source to either of the two branches. Let's say this is VOS. I mean, you can add the same voltage source here also in the inverting branch, it's all the same. Please notice that there is no voltage source sitting in the op amp, it is just a hypothetical modeling for our convenience, and these are the terminals that are accessible to you. To the outside world, this will be the minus terminal, plus terminal, and output terminal. Okay. And along with DC offset, we will consider one other non-ideality. So till now we have seen thermal noise in the course, and how is the power spectral density of thermal noise? It's a flat. So it turns out when we have MOSFETs, there is one other source of noise called flicker noise, also called 1/f noise. I will not go into the mechanism, but I will just say how its power spectral density will look like. So this power spectral density is inversely proportional to the frequency. Okay, so it will be a hyperbolic function like this. So the maximum energy is centered around which frequency? Around DC, right? So that is why we kind of combine the two and consider the two in the same way. DC offset is a DC. This flicker noise is also has maximum energy around DC, right? So anything that you do for suppressing the effect of DC offset will automatically reduce effect of flicker noise also. So we'll consider the two. And when I say I'm modeling this guy using a voltage source, assume that it also models the flicker noise. Okay. So let's consider.
MOSFET of the switch or the.
No, this is for the op amp. This is only for the op amp. Okay. So we'll consider each one and first understand what will happen because of this and see how to tackle. So I'll start with DC offset. And for that, I'll take a switch capacitor amplifier as an example. I'll not draw the complete circuit, I'll draw it in the two phases. In the phase phi1, I know that I am sampling the input onto the capacitor C1. What we do for this capacitor C2 in the amplifier? We reset it, we want to clear its memory completely. In phase phi2, what do we do?
Connect C1 to C2.
We basically transfer the charges in C1 to C2, and for that we take help of the op amp. Right, so this is C1, C2, and remember that this op amp now has a DC offset. So I'll just model it using a series voltage source at the non-inverting terminal. So this is the non-inverting terminal available to us outside this point, and in our circuit we are going to ground it. So we'll do this. I'll slightly redraw this so that it looks nice. I'll draw it like this. Okay. So again, first let's see what happens to the output. And what we'll do is, I'll assume that input is constant. We'll not worry about the time instance nts n minus half ts, so that it becomes simple for us. I'll assume that input is a constant voltage. We'll see what output we get in this case. Again, we get the output in which phase, phi1 or phi2? Phi2 is when charge transfer happens. So we'll apply charge conservation here. So where do we apply charge conservation?
And then negative
Here, right? And to start with, I'll assume the op amp has infinite gain. Let's not consider all non-idealities in one shot. We'll take one at a time to simplify things. The goal is to get some qualitative understanding first, and then we'll see how to go about
Then
it.
we can take A and then do solve and then put A equals to.
You can do, but that is going to complicate calculations, right? See, the moment you have big equations, you can't get any intuition out of it, right? First, let's get some simple things and see how we can expand it. So if I apply charge conservation, I'll look at the charges in these two plates. which are these. And before that, what is this voltage? VOS.
VOS.
So if I apply charge conservation, what do I get? What is the charge stored in this plate?
C1.
VOS into C1. Let's say this is Vout. What is the charge stored in this plate? VOS minus Vout into C2. And this is equal to the charges stored in the same plates in the previous phase. So we have to look at these two charges. It's minus C1 Vin. So I mean you can work out what do we get? Vout is C1 by C2 Vin plus you will get V offset times 1 plus C1 by C2. This algebra. And this should also logically make sense because
VOS 0.
VOS is applied at the non-inverting terminal. Loosely speaking, it sees like a non-inverting amplifier gain. That's why we have this step. So the effect of this op-amp's offset voltage is that it also introduces an offset voltage at the output, and the offset is basically amplified, right? So let's see how we can.
Should it be minus C1 by C2?
No. See, this charges here is minus C1 Vin, right? This minus C1 Vin charge is what will get transferred here, isn't it? Okay, let me get this up. So let's look at how we can go about solving this. And there are multiple lines of thought. So one is the following. So let me copy paste. Yeah. See here, the moment we had the offset in this circuit, what changed? Yeah, Vout changed, but what changed in the, at least in the equations, what changed?
The extra bias.
Yeah, I mean, let us say there was no offset, how will this equation change? I mean, if this offset was 0, what will change immediately?
The charge in the C2 is.
I mean, which voltage will, if I make this 0,
Virtual ground.
virtual ground will be 0 ideally, but now it is not the case, right? And what is, I mean, let's say I call this node Vx. What is making Vx to be equal to VOS here? I mean, here Vx is same as VOS, right? Why is that so? The op-amp and the negative feedback is enforcing. But mind you, the op-amp and the negative feedback, it just says that the potential at the inverting terminal is same as the non-inverting terminal, right? So the poor negative feedback just says V minus is V plus, which is VOS. It is us who have connected this node Vx to the inverting terminal, right? And ideally, if Vx were 0, things are all okay, right? So let me erase this. See, this potential is VOS that we cannot prevent at all, right? The moment you put the op-amp in negative feedback, we put, let's say here, this potential is VOS that cannot be prevented. But what we want is this node Vx must be 0. So obviously I cannot connect these two together. Make sense? So I'll basically do something here. And ideally you want Vx to be what? 0.
You're trying to make the.
We are trying to correct for it, right? Is that logic clear? The negative feedback is making the inverting potential to be VOS. In our case, we want this node where the two capacitors are connected, that must be 0. So which means I cannot simply short the two, I should put something in between. And look at this, here I have VOS, here I want 0 volt. Basically I want to reduce the voltage by VOS. What is the simplest element I can put here?
Put minus VOS.
I just put a voltage source with the right voltage. So in principle, if I were to go and put a voltage source like this with a value VOS, Vx will be 0. But of course I don't have voltage sources. What is the next best thing I have? I have a capacitor. I can charge a capacitor to VOS and put it there. So if I charge a capacitor to VOS and put it there, this should solve the problem. Clear? If I do this, Vx will tend to 0. Vx is basically the inverting terminal minus the capacitor voltage VOS. But again, this is the circuit in Phi 2, remember. Now the question is, how do you charge this capacitor to VOS? That's the only thing pending. So let's say I take the op amp. Let me push this down. Okay, let's say I take the op amp here, and I have the offset model like this. What is the simplest connection I can make here so that I can measure the offset voltage?
Series with the voltage.
Which one?
Capacitor should be.
I mean, forget about the capacitor for now. I have to get some voltage which is equal to VOS. If I get that, I can put a capacitor at that node and charge it. Right? The first goal is to get a voltage at one of these nodes which is equal to VOS. I can put in unity feedback like this. Right? So if I basically take the op amp and put it in unity feedback. Now again, this assume that this has infinite gain. So due to negative feedback, this potential will be VOS. So now I can go ahead and put the capacitor there, and now the capacitor will get charged to VOS. Set. And once this is charged, I mean this has to be done in phase phi 1, right? And then you can go ahead and put the capacitor like this and solve it. And remember, in phase phi 1, what are we doing to the capacitors C1 and C2? To the capacitors C1 and C2.
Yeah.
C1 is charging to input and C2 is reset. Yeah. I mean, this is what we need, right? In phase 1, this is something that has to be done. You cannot prevent that. In addition to doing this, you do this experiment to store the offset voltage in the capacitor, right? And this is one of the reasons why I told we want to keep the op amp free when it is not needed. In the last class, if you remember, we disconnected the op amp from the rest of the circuit by putting additional switches. Probably here. Okay. Yeah, these switches we added and disconnected the op amp in phase phi 1. And the reason was, one of the reasons is to do this. Okay. Great. So this will work, and here we have assumed that the op amp has infinite gain. So let us say this has a finite gain of A. So what will happen to this voltage? It won't be exactly VOS, but what will it be? Yeah. I mean, remember that, I mean, basically what we have is this, right? We have an op amp with a gain A, put in unity feedback, input is VOS, what is the output? A by 1 plus A, it's a basic negative feedback. So this will be A by A plus 1 times VOS. Approximately VOS if A is very large. So which means this voltage here is no longer VOS, it is, I'll just say, A by A plus 1 times VOS. And again, similarly, this voltage will not be exactly VOS. I mean, it becomes complicated to solve, but for now, assume that it's approximately VOS and see what happens. So we still assume that V minus is approximately VOS, and the voltage stored across the capacitor is this guy. So my new Vx will be the inverting terminal voltage, which we have assumed to be still VOS, minus the voltage across capacitor, which is A by 1 plus A times VOS. What is this?
Yes,
VOS by A plus 1, and for all practical purposes, this is VOS by A. Okay. So what you find is, if the gain is infinite, sanity check, it becomes 0. That's what we also saw. And if the gain is A, the offset gets reduced by the factor of A. So this voltage, if it was VOS, we got this as the output. Now this voltage Vx is VOS by A. So what will be the output?
VOS by A.
That simply gets divided by the gain, right? So in this case, the offset gets scaled by the DC gain. Okay. So this is the circuit in the two phases. Let's quickly draw the complete circuit.
What is the range of V?
Range of
V.
P is the input, right? It can go from 0 to supply.
Can you just, what is 0 from 0 to VDD?
VDD, yeah.
And what is the typical reading?
It can be anything, depends on the process, 1.8, 1.2, 1.8, whatever. Okay, so these are the circuits. I'll erase these things, you don't need it now. Let's quickly draw the full circuit. So in phase 1, I am charging the capacitor C1 to V in and discharging C2 to ground. So I'll just do that by putting switches here. This is 1E, this is C1, and C2 is discharged like this. And what are we doing to the op amp? Op amp is in unity feedback. So this is the op amp. Again, the offset is here. So I have to put it in unity feedback in phase 5.1. What should I do?
Connected to 5 switches with 1.
Is it clear? In phase 5.1, I want to put it in unity feedback. So I'll just put a switch like this. Okay. And what else? Yeah, this capacitor is getting charged to this potential. Right. So I'll draw like this, and this point is pulled to ground. Okay. This completes in phase 1. In phase 2, let's see each each element. So C1, the left plate is connected to ground. So I'll go ahead and put a switch to ground from here. Fine. And what happens? The negative terminal of this offset storage capacitor is connected to the right plate of C1. So what should I do? Basically, I want this plate and this plate to be connected in phi 2. So I'll go ahead and put a switch phi 2. Done. So that's only C2 is pending. C2 must be connected to the same plate here and output. So what I can do is here, right? So I can Great. So yeah, this is one way in which you can tackle for offset. There are several other ways. I'll give some of them as an assignment for you to work out. So now let's look at the other non-ideality, which is finite DC gain. And remember that when we tackle for this DC offset right now, even the flicker noise will get suppressed. Okay. So let's look at what will happen with finite DC gain. Again, I'll just reuse this now. So with finite DC gain, I will not consider offset because we know how to tackle offset. Op amp has no offset. This has a gain of A. So what will change now in the circuit? I mean, let's say I want to apply charge conservation. I need to know this voltage. What is this voltage? Huh? V out by A or something else? The output voltage is V out. Non-inverting terminal is grounded. What is the inverting terminal? I mean, for the op amp with the gain A, what is the relation between V out and the inputs? A times. I mean, what minus what?
Positive terminal minus.
Positive terminal is what?
That's a ground. You will get minus V out by A.
This is Vx. So what is Vx? Minus V out by A. Okay. So here, let's say I call the error voltage. It's minus V out by A. Fine. Okay. So I mean, with the offset case, this voltage was VOS. So right now it's minus V out by A. We already did the calculation when we had offset. So should I do the calculation again, or can I do something simple? I'll replace VOS by minus V out by A. That's all. Okay, so if I do this, I'll do it here itself. It's minus V out by A. And then you can club terms, and I'll just give the final expression. Hopefully it will look like this, A beta by 1 plus A beta, where beta is C2 by C1 plus C2. Beta is basically the feedback factor from V out to this node, and here you see a capacitive division here. So if this is V out, this voltage will be capacitive division, which is C2 by C1 plus C2. Okay, and this should also make sense. It's a negative feedback, so you see the same term a beta by 1 plus a beta term. Great. So now let's see how we can tackle this. Now remember that this situation is very similar to the offset case, right? Ideally you wanted this voltage to be 0. So that is the voltage where we are connecting the two plates of the two capacitors, right? But in earlier case it was VOS, now it is some other voltage. And for the offset case, what we did was we tried to disconnect these two and put an appropriate voltage and try to bring it to 0. So right now what can we do?
Same method.
We can do something similar, right? So let's say I take this. Basically the problem is, again, if I connect these two, remember that the negative feedback is forcing the inverting terminal to minus V out by A, right? It's this forcing to minus V out by A, and we want this voltage to be 0, so we better not connect this. So instead of connecting these two, what do I put now? We will put a capacitor charged to minus V out by A. I'll just put here. So this is charged to minus V out by A. Okay. So this is V out. If I do that, I expect that this Vx will tend to 0. But yeah, now the question arises, how do I get this estimate of minus V out by A? How can I get estimate of minus V out by A? I mean, here I have drawn some circuits, right? In which of the circuits I can get minus V out by A?
Again, unity feedback will give it minus.
If you put unity feedback, how will I get? If I put unity feedback, this what will I get? I mean, the circuit that we have drawn, I have drawn some circuits, right? In which of the circuits I can get this voltage minus V out by A? Is there any node in the circuits that I have drawn on this paper where one of the node voltages is minus V out by A?
Here,
This guy, here it's minus V out by A. Okay. So, which means I can go and put the capacitor here. So now the capacitor will charge to minus V out by A. Okay. Is that clear? But remember that before doing this, I also have to charge the input capacitor to V in. C2 must be reset. So I also have to do this. And even the capacitor on which we are storing this error, that can be reset, right? We don't need to. So basically, how many phases I need?
how many?
Clock phases I need?
3.
I need 3. Basically, I have 3 modes of operation. One, in which I just initialize all the capacitor voltages. Second is when I try to get an estimate of the error voltage. In the third phase, I go and correct it. Okay. So this is, let's say, phi 1, this is phi 2, this is phi 3. Please note that in the offset correction case, we had 2 phases, and that was possible because if you look at the error induced by the offset, this guy is independent of the input. Okay. So basically, when we are sampling the input itself, we can actually hook up a circuit that can give an estimate of the offset. Okay. So that's why this input sampling and the estimation of the error voltage, the two operations can be combined. Whereas here, the error we get, this guy is dependent on the input, right? So which means until I do a charge transfer once, I will not know what that error voltage is. So the process of sampling the input and estimating the error, they cannot be combined. So we need to have 2 separate phases for them. Clear? Great.
So 5 3 even the third clock as well as the second clock will be
Everything must be non-overlapping. See, when I have,
then C1 will get detached, right?
that's okay, it can be detached, but if it's detached, it is okay. We are not disturbing the charge.
We are not changing the V out.
That's
but
okay.
We'll then remove C2 also because that also has phi2 in it.
Which one? No. See,
Phi3 may use.
we want C2 to be connected like this in phi 2. We want C2 to be connected like this in phi 3. We have to hook up the circuit like that. That's all.
Acha, but
See, this,
How can I
don't
connect
overthink. Don't overthink. In phase phi 1, in one of the clock phases, the circuit must look like this. In one clock phase, the circuit must look like this. In the final clock phase, the circuit must look like this. This is what we have come up with. Let's come to the final circuit later. This point clear? So okay, then now that should raise this question. So here I assume that the error voltage is minus V out by A. So if I exactly put this voltage here, so will this become 0 exactly? Why?
because
I mean, at least logically it makes sense that, I mean, ideally it should not become 0. If it becomes 0, it means somehow we have got infinite gain from the op amp.
V out will change because when we'll give when this join the V out will automatically change.
Exactly, right? See, here I assume that the two V outs are same. But these two will not be exactly same, right? I mean, in fact, the reason for doing this operation is that we hope V out reaches more closer to the ideal value. So what we get in the second phase, it is some V out hat. So the error we store is an estimate minus V out hat by A. So here also the voltage stored is minus V out hat by A. So the Vx voltage will be the inverting terminal voltage. And remember, what is this voltage?
This is like minus V out by
Minus V out. I mean, this is the output voltage V out. Gain is A, so this is minus V out by A. So Vx will be minus V out by A minus V out hat by A. Okay. So it will not be exactly 0, but let's say close enough to 0. So that's why it doesn't exactly become 0. So we'll see how much improvement we get shortly. But before that, let us say the op amp here also has a DC offset, which is what will be the case in practice. So do you think the DC offset will get corrected or no?
can get corrected.
Why?
This
I mean, what did we look for? I mean, for the offset correction, what were we doing?
we're charging the capacitor.
We, I mean, if we
Same thing.
see here, if this has a DC offset, approximately what this voltage will be? It will also have information about the offset voltage. Because of the virtual ground, we will not only have information about this guy. Remember that this potential will not just be minus V out by A. It will also have information about VOS because the output is VOS minus this into A. So even this capacitor will now store information about the offset voltage. So when you put it like this, the offset also will get reduced to a lot. Exactly, don't get cancelled.
Offset will get cancelled, right?
In the last case also we saw it doesn't get exactly cancelled. We can't get a complete estimate of the offset voltage. We have a finite gain, so you can't exactly find what that offset voltage is. You can only get an estimate of the offset. Is that okay? So here we get two things. We can correct for the gain error, that is the finite gain of the op amp can be tackled, and also the offset gets correct. And let's see how much we can get improvement. So in the offset correction case, yeah, there also we had the same thing, right? So we stored the offset across capacitor and connected it like this, same principle. So in this case, this virtual ground voltage was VOS, and after we did the error correction, it reduced to VOS by A. So the error voltage was VOS and it became VOS by A. In our circuit, the error voltage is minus V out by A. After you do this error correction, what do you think this will become? Minus V out by A square. Same principle. I am just giving a qualitative explanation. So the error voltage which was initially say minus V out by A, till now become minus V out by A square. So it means what is the effective DC gain we have achieved? No. I mean, if we had a DC gain of A, see, when we didn't do anything, this had a DC gain of A, we got minus V out by A. Now, after doing this, I am qualitatively saying that this will become approximately V out by A square.
How do you know V out by A square?
That's the logic, right? See, I understand qualitatively, right? If you try to derive it, it's going to be messy.
Okay.
You understand qualitatively, please. So, this earlier in the offset correction case, the error voltage was VOS, and we analyzed clearly and saw that after correcting it became VOS by A.
Yes.
So now we are doing the same principle. The logic is same, right? So here the error voltage is minus V out by A. After doing the error correction, it's minus V out by A square.
A square.
So what is effective DC gain?
A square.
A square, right? So we have increased the DC gain from A to A square. Okay.
So effective DC gain in the sense that if we have it, if that is equivalent to another op amp,
Exactly.
which
Has a gain of A
when
square.
have any of these considerations,
Exactly.
then it must have A square.
Exactly. So let's say we take an op amp with the gain of A and do all this thing, and take an op amp with the gain of A square and directly connect it like this. We'll both get the same output. Capacitor is there. So here we don't do anything and do it like this. Both the outputs will be same in steady state. That's the principle. I mean, that's the idea. Clear? And we also saw that in this case offset also gets corrected. So offset also will go as VOS by. So again, this is the circuit in 3 phases. Let's quickly make the complete circuit. Okay, this okay, yeah. So let's try to make the circuit. So in phi 1, the capacitor C1 is connected to V in, C2 is discharged. Let me call this guy to be CB. And remember that we have 3 phases. In the first phase, basically we are sampling the input and initializing all capacitor voltages. Second phase is when we are estimating the error. And in the third phase, we are doing this correction. So let's draw the circuit. In phase phi 1, I'll draw slightly down. The capacitor C1 samples the input. Done. C2 is reset. Done. And CB is also reset. So let us say CB finally will be connected like this. So I'll draw it like this. Okay. In phase 2, what we are doing, we are connecting the left plate of C1 to ground. Okay. And what happens? Yeah, the top plate of CD is connected to the inverting terminal of the op amp. So if the op amp is here, in phase phi 2, I'll connect it like this. Okay. This is ground. And also the right side plate of C1 is connected to the left plate of C2 and top plate of CB. Right? So this is the right side plate of C1. I have to connect it to the top plate of CB, which is here, and this guy. Okay. So what I'll do is this. So let's say take a switch. This will connect. Oops, sorry. So this will connect basically these 2 plates. I also have to connect this node to this guy. So I'll try to put another switch here. And C2 is connected to the output of the op amp. Okay, and the last phase, what I'm doing, in the last phase, left plate of C1 is still connected to ground. So I'll just say that this is phi 2 3. It means the clock is active in both phi 2 and phi 3. Okay. And okay, one thing is, yeah, the bottom plate of CB is connected to ground in phase phi 2, right? So this is the bottom plate of CB. Even in phi 2 it is grounded, so I'll put as phi 1 2. In both phase phi 1 and phi 2 it is grounded. That's what is this. And the right plate of CB is connected to the bottom plate of CB. This is the bottom plate of CB, right plate of C1. I have to short the two. One more switch. Okay. And finally C2 connection will change. So C2 will now connect to right plate of C1. So this is C2. I want to connect it to here, right? So I'll go ahead and put one more switch like this. Sorry. And finally, this guy has to connect to the output still. So it is already connected in phase phi 2. So I'll just say it's phi 2 3. So that in both phases it's connected. I mean, this is just simple logic. There is nothing there, right? Look at the circuit and hook up the circuit. And this principle is called correlated double sampling. Abbreviated as CDS. Okay. And basically, even the offset correction technique that we saw, that had the same principle, right? Because there also, in one phase, we were trying to estimate the error and try to correct it. So this is also based on correlated double sampling. And the name comes out because if you look at the underlying principle, we are basically sampling twice, one to sample the input and one to sample the estimate of the error. And with that estimate, we are doing correction, right? And it's correlated because if you think carefully, the error is estimated in one clock phase phi 2 and we are correcting that error in the other phase. The assumption is that the error doesn't change in the two phases. I mean, in this case, it makes sense because we have already sampled the input. For that input, the error is same. And even for DC offset, the DC offset doesn't change from clock phase. So the DC offset is also the same. Sorry? This one. Okay. So see this, I mean, this is basically you look at each element and then see how it is connected in each phase. So here I find that C1 is connected like this. So I put a switch. Okay. So I'll do it at the end. Okay. This is basically simple look and do. I'll explain to you at the end of the class. Huh? Oh, working. I'll just show it, explain here. See, did you understand the principle? The principle is if this potential is 0, we are all set. And this principle, I mean, this voltage is non-zero normally because the inverting terminal is set to minus V out by A by the op amp, and we are connecting this node to the inverting terminal. So we are coupling it, I mean, decoupling it by putting an appropriate DC shift there, right? And that voltage must be the error signal minus V out by A. So first we have to understand what minus V out by A is and charge a capacitor to that voltage. And that cannot be done, we cannot get an estimate of this minus V out by A unless we do a charge transfer once. So you do a charge transfer with C1 and C2 with the op amp, then the virtual ground node will have that error signal information, you sample it, and once you have it, you put that here, right? And before doing the charge transfer, obviously you have to sample the input and reset the capacitor, so that will demand one other clock phase prior to this. Okay. And the reason we have the third clock phase is in the offset case, the process of sampling the input and estimating the error can be combined because offset is independent of the input. So when we are sampling the input also, we can estimate the offset, but here you can't do it. Okay. Is that clear? So again, it's called correlated because, yeah, as I was mentioning, the error in the two phases are correlated. And if you look at flicker noise, I told we'll consider along with DC offset. It has a very high energy around low frequencies. So it is not from phase 2 to phase 3, it will not be exactly same, but there will be a very high correlation in the noise sample from this to this because it mostly has low frequency. So any correlated error or correlated noise will get suppressed by this guy. Okay. So I'll just explain one other commonly used technique. Just copy paste this once. Yeah. Okay, let's say this. So there is one other principle which is commonly done. I'll not assume offset for now. Let's say this is 0. Again, the idea is to try to increase the effective DC gain of the op amp, and that is possible if you make this guy to be 0, right? So what I'll do, I'll first erase this. Give me a second. See here, what is the inverting terminal potential? Huh? No, I mean finite gain, right? I mean, what is the inverting terminal potential? Minus V out by A. Should be. Okay, it's not minus V out. It's just that line which didn't get erased. So it's minus V out by A, or in principle it is basically the op amp output by A, right? I'll just say minus V op amp by A. And in this case, I have connected the op amp output to my output. Okay. Now let us say I connect the inverting terminal to the node Vx directly like this. So now if I want to make this go to 0, what should I reduce? Vx is minus V op amp by A. So basically see, this Vx is basically set by the output of the op amp, right? If I were to reduce Vx, what should I reduce? The op amp has to be reduced. And in principle I want to, this must be 0, so what should this be? 0. But if, which means I cannot connect the output to the op amp output directly, right? So the idea is same. I'll decouple these two. I'll put something. We'll get the correct output and try to force this guy go to 0. So what will you put here? A capacitor charged to the output voltage. Simple. So again, the principle is all same. We put a capacitor charged to the output voltage, but I can't get the exact output, so I'll get an estimate of the output, and I can get an estimate of the output from the previous phase like this. So here, where should I put the capacitor? This capacitor. Where should I connect this capacitor in this circuit? Huh? From which point to ground? From the output to ground I'll put it, so that it will acquire the estimate of the output.
So what current flows into and outside the output terminal.
Correct. Yeah.
So Vout cap also changes.
That is true. So Vout had changed, so that's why you have to size the capacitor appropriately. If let's say the capacitor is sized appropriately large enough, then you actually, even if some current is down, it might not lose its charge. Yeah, you are right. So there is some other additional considerations. I'm not going into details there.
But getting a high capacitor will be.
No, basically the thing is, usually in most of the applications, the load capacitor might not be really large, as we see in ADC's cases. If this has a large enough gain, the load capacitor will usually be not very large, and you can actually work out and see. I'll refer you to the paper, but what you mentioned is a problem. But let's not worry about that for now. Right? So basically, I'll put the capacitor here. That will charge the capacitor to an estimate of my output. Then I subtract it. And this technique is called correlated level shifting. Abbreviated as CLS. So here again, this virtual ground will not exactly go to 0. So again the effective gain will become from A to A square. Okay. And yeah, I mean you can draw the complete circuit from this. I will not do that. Okay. So there are, I mean, pros and cons for both CLS and CDS. So one thing is, see in this correlated level shifting, if let us say the op amp has an offset voltage, do you think we'll be able to correct it or no? Remember that in the all our offset estimations were based on the fact that this voltage stores information about offset. If we charge the capacitor from here, we can get information on offset. But since we are doing at the output side, we can't get any information about offset. So this doesn't correct for the DC offset. Okay. So that is one one difference. CLS, I'll just say offset, and for that case flicker noise, it doesn't correct. But the advantage is, so let's say in the double sampling technique, yeah, in the earlier case, double sampling, so we added additional capacitor and switches, right? And remember that the moment I add any switch and a resistor, the resistor models the on resistance of the switch. The resistor will generate noise. So what will be the mean square noise across a capacitor if this is CB? It will be KT by CB. Okay. And in correlated double sampling, this noise is added at the input of the op amp, right? So you can think of it as the noise is getting added at the input. Again, very rough explanations I am giving. This is KT by CB. In level shifting, we are adding the additional capacitor at the output side. Okay. So here again we will have some switches at the output side. So that will again introduce noise, and the noise variance will be KT by C. So let us say I call it CCLS. So here again noise will be there, but at the output side, this is KT by CCLS. If this has a gain of A, if I refer it at the input, what will happen? This is Vn. What will this be so that both these guys are same?
A times 1 by A times.
This will be Vn by A, right? And this is mean squared value. So the effective input referred mean squared noise value will be KT by CCLS to by A square. Yeah. So that is one advantage with CLS over CDS. Again, there are fine points. I will point you to the paper so that you can see if you are interested. And one issue is what he mentioned. If you try to draw the load is large, and if you draw a lot of current, this voltage can get disturbed. Okay. Great. And yeah, so what we can do? Yeah, probably I can show you how we can analyze this CDS circuit. Okay. So here I qualitatively show that the gain increases from A to A square, and you can also actually analyze it using charge conservation and prove it. I'll quickly show how we can do that. I'll not derive it fully. So again, we are doing charge conservation, and the output is finally available in which phase? Phi 1, Phi 2 or Phi 3? Huh? Phi 3, right? So I will be interested in the output in Phi 3, so I will apply charge conservation there. Here I have two nodes to apply. I can apply charge conservation here or here. So let's say I start with Vx node. So what are the charges? Yeah, C1 Vx. What about C2?
C2 Vx minus V out.
Yeah. Plus CB Vx. Is that okay? So this will be equal to the charges stored in the same plates in the previous phase. In the previous phase, what are the charges? No, I mean this minus V out hat by A. Minus V out hat by A into C1. For C2 it is minus V out hat by A, V out hat. And for CB, be careful, here we looked at the bottom plate, so here also we should look at the bottom plate, right? And what is the charge in the bottom plate?
CB into V out hat by
Top plate was minus V out hat by A into CB, bottom plate will be negative, it will be plus V out hat by A, CB. So now I am interested in V out, so I need to find Vx and V out hat. So Vx is the voltage here, so I'll have to apply charge conservation in this circuit in some other node, and we already have that node which is here. If I do that, what do I get? I just have one capacitor connected, no charge flows into the op-amp input. So what is the charge in the capacitor CB? This minus V out by A
minus Vx of
CB, that is equal to, this is the top plate of CB, so here also I look at top plate of CB, which is,
minus V out hat by A into CB.
that's all. That's all. I mean, here looking at only this plate, only look at this plate. Okay. And yeah, that will give us Vx. And to find Vx also we need V out hat. V out hat is the voltage in which phase?
V out hat is in the
Second phase.
second phase.
I'll have to apply charge conservation in the second phase circuit. Only one node is there. I'll apply here. What do I get?
We get minus V out by
Minus V out hat by A into C1.
C1
C2 it will be minus V out hat by A minus V out hat. Okay.
plus
And
minus
minus V out hat by A
into CB
CB.
equals
This will be equal to the charges stored in the previous phase, and except C1 all caps are reset, and we are looking at the charges stored in this plate.
minus C1 equals
That's all. Okay. So basically we have three unknowns, right? Vx, V out hat, three equations. Third equation. Can basically sit and solve. I mean, it's just messy algebra. You can use any symbolic calculator and solve. And finally, you will find that the gain you get is C1 by C2 times some A square by A square plus something. That means effective gain is, A square. That's all. You can do the same thing with the CLS also, and solve it. You will again find that the gain is of the order of A square. Great. So I just want to discuss one other technique, and yeah, maybe I'll do it differently. So I'll not derive it. I'll just show the circuit. We'll understand how that technique comes about, right? I mean, that's how will happen in practice. You will come up with something. I mean, you will look at some circuit, and we'll try to understand how that circuit works and understand the basis of that circuit, right? So this circuit is for offset correction, only for the offset voltage. So in phase phi 1, let's say the circuit is looking like this. In phase phi 2, okay, op amp has offset, so I'll model the offset voltage here. In phi 2, it's the same, no difference. Okay. Yeah. So the claim is offset will get corrected, and again, you don't have to initially assume finite DC gain. We are interested only in seeing what happens to the offset. So to simplify things, assume it as infinite DC gain. And the circuit is pretty simple, so we can quickly analyze. So I am interested in the output in phase phi 2. So let's do charge conservation. What is this voltage? Virtual ground? POS. If I apply charge conservation, what do I get? BOS C1. Let's say this is V out. For C2 it is what? VOS minus V out. So this is say equal to the charges stored in these two plates in the previous phase. And what is that? This voltage is also VOS, remember? VOS minus V in times C1 plus, I'm sorry, hold on, let me mark it. VOS times VOS minus V in times C1 plus VOS times C2. If you solve for it, this VOS C1 gets cancelled, VOS C2 gets cancelled, you'll only end up with this guy, right? So output is exactly C1 by C2 times Vin, and there is no offset. So what is the magic that's happening here? I mean, this is the circuit. If you analyze it, we are able to verify that it works. But what is the basis behind the circuit? What is the logic? I mean, the circuit operates in two phases, right? Right? You look at the two circuits in the two phases,
The
and
charge stored in C1 is not V in C1, but it's V.
yeah, basically the circuit is different only in this phase, right? In phase phi 2 it is all the same. The only difference is here, and in phase phi 1 normally what do? We charge the capacitor to V in, C2 is fully reset. So usually if you have to do conventionally, what will be this charge?
It's just C1 V. That's
Plus or minus C?
minus.
It will be just minus C1 V in, and for C2 it will be 0. But now what we are doing is, we are trying to charge C1 not to minus V in plus VOS. And reason is, see, the conventionally if you do, the initial charge stored, let's say initial charge in C1 in this plate, conventionally what is that? Minus C1 V in. And what is the final charge? Final charge in C1 is what?
After the torque.
Here, right? What is the final charge in C1?
VOS by C. VOS
VOS into C1. And remember, only the difference in the charges will get transferred to C2. So the delta Q will always be whatever, VOS C1 plus whatever, right? Something, I mean, you can find out, right? This is the difference between the two. Now remember that this is something I cannot prevent. Because of the fact that the op amp has offset, this voltage is set to VOS. The final charge is always C1 V in. So this is fixed, let us say. But you want delta Q to be exactly C1 V in. So which means you need to add this extra offset here. So which means the voltage C1 that should voltage to which C1 should be charged is VOS minus V in and not simply V in. Same is the case with C2 also. Normally C2 is completely discharged. Here we discharge it with respect to VOS. That's okay?
This is a simpler charge.
But this corrects for the DC offset but not for the gain, right? But let's look at what can be done for the DC gain.
But gain is already in 8,000. Basically, not small amount per
Yeah.
1,000 gain.
No, so small op amps do not have thousands. I mean, you can make op amps with thousands, but that will take a lot of power. To get
Normally,
a
non-ideal op amp will have.
see, you can make op amps with 80 dB, 100 dB also, 1000 and 10,000 also, but it takes a lot of design effort. And if you wanted to operate at high speeds, ensuring good linearity, it will take up a lot of power. On the other hand, designing a simple common source amplifier or a simple differential amplifier with a gain of 10 or 20 is simple. That's much simpler, right? And it will take much lesser power. So which means you can, for the smaller power, you can basically get a higher gain.
But then complication will come here.
There is no complication, you just add a couple of switches. I mean, it is all about burning more power or adding more switches in your circuit. Right, so this is the logic here. So let's try to use the same logic. And here remember, only the offset is getting corrected. Right? So let's see if we can extend this principle to correct the finite DC gain also. So yeah, let's see. So for correcting the offset, the principle they used was, instead of sampling the input with respect to ground, we sampled it with respect to the error voltage we will have. For the offset case, it was the offset. Now I am trying to correct for the gain error, right? So basically, if I normally do this, C1, C2, this is V out. What will be this voltage if this has a gain of A? Minus V out by A. So we'll try to use the same principle, right? So here we are sampling the input capacitor and discharging the output capacitor C2 with respect to the virtual ground error voltage. So here the error voltage is this guy. So what should we do? I mean, here we sampled the input with respect to the error voltage. The error voltage is here. So what should you do now? We have to sample the input and reset one more capacitor with respect to minus V out by A. And remember, to get this voltage itself, I need one C1, C2. Now which means I need to take another capacitor, charge it to V in with respect to this voltage, another capacitor C2, discharge it to ground with respect to that voltage. The logic is same. I want to obtain this error voltage and then do this thing. For an offset case, it's simple, but
This circuit will solve both the problems.
to some extent, yes. So let's finish the circuit, right? So here, to get the error voltage, I need to do a charge transfer once with one set of capacitors C1, C2. If I do that, I'll get the error voltage here, right? But then, using that error voltage, I'll sample the input and reset the capacitor. So basically, we need one more set of capacitor. Okay, so let's say I call this C1 hat, C2 hat. So finally, what should I do? I'll do charge transfer with C1 and C2. So I'll take this. Now I'll okay. So when I let's say this is one phase phi 1, this is phase phi 2. When I'm doing charge transferring with C1 and C2, what should I do for C1 hat and C2 hat? They should be disconnected. Yeah, it's disconnected from the circuit, but what should they be connected to? I mean, remember that in phi 1, the goal is to establish this error voltage. And to establish the error voltage, in the previous phase, what should the capacitor C1 hat be charged to? Okay, see, how can I get the error voltage? See, first of all, how can I get, I want an error voltage which is minus V out by A. To get the error voltage, first, what should I do?
Negative.
No. From first, what should I do?
V out should be V out.
Yeah. How do I get V out?
Achha.
That's the first thing, right? Yeah, you should get V out. How do I get V out first?
Put input.
Input where? Yeah, basically I have to sample the input and reset one capacitor. This is one phase. In the next phase, I will do this. Okay. Now I can get this voltage error. So now with respect to this voltage, I will be charging another set of capacitor like this, right? And in the next, in this phase, basically I'll do charge transfer with respect to the new capacitors. Okay, this is, let us say, C1, C2.
So the previous thing should be connected to V.
That's all. So this is C1 hat, C2 hat.
C2 should be recharged.
So this is, let us say, phase phi 2. In one phase, the let's say I call dummy capacitors. These dummy capacitors must be charged to V in and reset. And in that phase, we'll be doing charge transfer with our actual capacitors. And in the succeeding phase, we'll do charge transfer with the dummy capacitors. And that we are doing to establish the error voltage. And with respect to the error voltage, we are actually sampling our actual capacitors. Okay. This is cyclic operation. So here, what should I do? Basically, I have to take V in, sample C1 hat, and C2 is grounded. So here, first we do this, do a charge transfer. And once we do the charge transfer, we get the error voltage. Then you do the actual sampling with respect to the error voltage, and then you do the final charge transfer. So this will again try solve the gain, but there is one catch. So here if you look at it, the dummy capacitors are sampling the input in phase phi 2, right? And the error voltage we are obtaining here is with respect to the input sampled in phi 2. But the actual capacitors are sampling the input in which phase? This is the actual capacitor. In which phase it is sampling the input?
In the 5 2.
No. So please,
In the 5 1.
in phi 1. So basically this is assuming that the input doesn't change a lot from phi 1 to phi 2. Because we are obtaining error voltage with respect to the input sampled in phi 2, right? And the actual capacitors are sampling the input in phase phi 1. So this will work as long as the input doesn't change a lot from phi 1 to phi 2, right? So that is the catch with this. But whereas in our other techniques of double sampling and level shifting, we don't have that issue. So that's why that is a limitation of this. Cool. I think we are running short. Let's stop here.